Good day, everybody, and a warm welcome to this webinar about NanoLund and nanoscience. My name is Maria Johansson, and I am an Alumni Relations Manager here at Lund University. It's great to see you all popping into our webinar again. I'm soon going to hand over to our key speaker for this event, Ms. Maria Messing, Associate Professor in Material Physics, who's going to give you a session on nanoscience and NanoLund. First, I would just like to give you some short information about our upcoming events. This is one of our events for the fall program for alumni. And I'm going to share my screen with you again. So, as I mentioned, this is one of our first events for the fall semester, but we have more exciting things coming up. The Alumni Book Club is once again being presented by us. We are doing a crime fiction season. We thought it was a good idea to have the autumn season as a crime fiction season. And we are both going to host events in Swedish and in English. So our first event within the book club is on 27th of September, where we're going to talk with Kerstin Bergman, who is a crime fiction expert and associate professor here at Lund University, who's going to give you an overview of the Swedish crime fiction landscape. And then we're moving on to Karin Wallberg, who is a crime fiction author and also alumni from Lund University and doctor as well. And she's been writing books in both English and Swedish, and we have a book, her latest book in Swedish, A God Man, and a session about one of her English books, The Death of a Carpet Dealer. On 8th November, we're going to talk about Handbok I Lundandan, the spirit of Lund, does it exist? And on 17th November, we have another author talk with new author Anna Agrell and her first book, Ett halvt andetag. Secondly, if you have any kinds of questions about the alumni network or ideas about our activities, you're very welcome to send us an email. Check out latest news and the event program on our website. The Swedish one is lu.se/alum, and the English one is lunduniversity.lu.se/alumni. You are also welcome to follow us on LinkedIn and on Instagram. Of course, you can also find us on Facebook. So there's multiple ways to get in contact with us and stay up to date about what's going on at your alma mater. Some housekeeping rules for this event is that if you have any questions, since this is a webinar, we can't see you. You can see us, hopefully, and hear as well, but we can't see you. So if you have any questions, which I hope you have, you're welcome to use the Q&A function that's available in the bottom bar in your Zoom window. If there are any links or important information from us, you're welcome to write in the chat. And our speaker, Maria, she also mentioned that if you have any comments or anything like that, you're also welcome to post that in the chat, and I will keep track of that during our session. This webinar is recorded and will be available through Lund University YouTube channel, and we will send you a link with to the recording within a few days' time. That email will also include a survey, and please give us your feedback on other ideas of events and anything else that you would like to share with us. And with that, I think I am going to hand over the screen to our speaker. A warm welcome to you, Maria Messing. You are Associate Professor in Material Physics and also in charge of many things at NanoLund that you're going to give us more knowledge about. So without further ado, I'm happy to give the screen to you.
Thank you very much. I saw somebody already wrote it's a bad sound, so I hope you can hear me anyway. So thank you very much for inviting me to give this presentation. I didn't even know that there was something called Lund University alumni thing, so I'm also learning a lot today. I'm here to talk about nanoscience and nanotechnology, and the reason I'm doing it is because I'm representing NanoLund. And NanoLund is a strategic research area from the Swedish government, so the Center for Nanoscience within Sweden. But I will talk a little bit more about that in the end, because I think we start with the interesting, and that is research and what is nanotechnology. I'm not sure about your background. I think it's very different. So if something is unclear, just write in the Q&A during my talk, and I hope to get some help with the questions from Maria if I don't notice them myself. So to start, nanotechnology is quite broad because it's actually talking about research or things that are happening that has a certain length scale of nanometers. So that can be very multidisciplinary, from electronics to what is happening in nature, medicine, biology, chemistry. So it's a quite broad topic. And we are talking about very small things. If we look here in this scale bar, let me see if I can get a pointer somehow. Yes, a laser pointer. Now I feel comfortable again. So on the top of this length scale is 1 centimeter, which for me is normally something pretty small. But when we're talking about nanotechnology, it's actually huge. So we have to go down several orders of magnitude. If we just go down to millimeter, here we find stuff like the width of our hair. And that is also something very small, but still something that we can see with our naked eye. Then we go down to the micrometer scale. That's 1,000 times smaller than millimeters. And then we find stuff like red blood cells that are about 2 micron thick. And then we have to continue further and further down to the scale where we are at 10⁻⁹ meters. That is 1 nanometer. And one should not confuse it with atom physics, where you're talking about a single atom, because 1 atom is about 0.1 nanometer or 1 angstrom. So we're talking about a bunch of atoms doing something. And if we look in nature, we have here silicon atoms. It's these dots is actually single atoms, what you see. And this is stuff on the left side that we have in nature. But what we can do with nanotechnology is that we look here on the right side instead, where we can make structures that are this small and manipulate matter at this length scale. So we're talking about 10⁻⁹ meters. That's 1 nanometer. And one can ask, why are we so interested in this length scale? Why nanometer? And one thing is that in biology, we have very many interesting structures in this size range. So here I show DNA, which is about 2 nanometers wide. And now I guess we have learned recently a lot about virus that is also about 50 to 100 nanometer sized. So we're talking about a length scale where many important things happen in biology and in our bodies. At this scale, we also have something called quantum effects. So to simplify, one can say that the materials do not behave the way we are used to them behaving. So what I'm showing here as an example is some bottles with liquids of different color, but actually they contain the same material. It's a small little nanoparticle, and just by changing the size from 2 to 10 nanometers, it can sort of emit light with different wavelength. So at this scale, the material is the same, cadmium selenide, but by changing the size of these particles, we get all different colors. And this is, for example, what you have in these quantum dot TVs that you might see in the store these days. And I have to stress that nanometer is so small that we have trouble really relating to it. We know very well what a meter is and a centimeter and a millimeter, but nanometer is so small we cannot see it with our naked eyes. So as an example, your nails they grow by 1 nanometer per second. And I'm pretty sure that you don't notice that your nails grow. Another interesting thing with stuff on the nanometer scale is surface effects. And you might wonder why I have this little animal here. It's this gecko, you know, that can climb on walls and climb in the ceiling. And with its own body weight, it doesn't fall down. And for a long time, researchers were puzzled. How could they do it? Did they have some kind of suction thing under their hand or feet, if you call that for a gecko? But no, it didn't. It's actually due to these small structures that we find in nanotechnology. So when strong enough microscopes were invented and people started studying the gecko feet, they could see that it contains millions and billions of really small hair. And every time, if we have something like my finger touching a surface, there is a small force between my finger and a surface. It's called van der Waals force, but that's not so important. It's a very, very weak force. And I don't have many contact points when I have my finger to my hand. But if I had, like the gecko, millions of these nano hairs, we have millions of contact points. So even if the force in just one point is very weak, if we add these up, the force will be strong enough to carry the gecko, so it can carry its own weight. And these days, people are trying to do this artificially. So you do what you find in nature. So you make like tape that sticks very well, that is just nanostructures, no glue or sticky stuff, but just by the structures, you can get very good adhesion. And researchers, for example, think this might be used in outer space where you have problems with the gravity and so on. We can look at another example in nature where we have these nanostructures, and that is the lotus leaf. It's a leaf that is called to be self-cleansing. It cleans itself, and that's because it's super hydrophobic. It means that a drop of water cannot wet the surface. The water droplet will stay like a drop and pick up the dirt when it's rolling over the leaf. And the reason for this, you can see, is these small micro and nanostructures. I don't know why my PowerPoint is living its own life, forbidding the water droplet to wet the surface. And this is another thing that you want to do, what we do in nature with nanotechnology, so you can use this to make surfaces with these properties so that they can be self-cleaning. And I have a small movie. I will see if I manage to start this. No? Huh. So here you see just the surface where you have these nanostructures. And what happens, so here you have an untreated surface and a surface with nanostructure. And you see this super hydrophobicity, that the liquid doesn't really wet the surface. It just rolls off the surface. And here is another example just to show what it looks like when they have put this nano stuff on the side, which means that the droplet here will not stay, it will move into the center. And this is one thing with nanotechnology, and this is surface coatings and surface structures that is used for this self-cleaning properties, where basically the water will take away the dirt. So we can ask ourselves, why have we started talking about nanotechnology, since apparently this length scale or these structures and the idea have been around in nature for a long time. And the reason is that some decades ago, we started to be able, we had the tools to both view what is happening on this nanoscale, because with conventional microscopes, you cannot get the resolution to see such small objects. So you got better microscopes, and you could also design and manipulate matter on this scale. So what we see here, all these dots, especially in this little movie, it's single atoms. So here are researchers, they have played with single atoms and created what they call the world's smallest movie. Now it's getting a bit old, but I still think it's so fascinating that you can do this stuff. You can take atoms and move them around and do what you like with them, basically. So this is the reason we have these tools. Okay, good. It seems like people can hear me. It said in the chat. So this is why people started talking about nanotechnology, that nowadays we can work on this scale. And then people usually ask, so when does it come? When is nanotechnology affecting our lives? And the answer is, it already is, to a large extent. You find nanotechnology all around you. I assume most of you have something like this. Now we cannot see it because I have a virtual background, but the phone I was trying to show you, and you probably sit in front of a computer. So an example of how fast it is here. We have this, I just used my arrow, this ENIAC, the first computer, and it was huge. It weighed 30 tons, and it has 20,000 vacuum tubes inside it. And it could do basically nothing if we compare today. And now we have these, our phones, that is actually not maybe a phone anymore. It's more of a small computer where we instead have something called transistors within them. And we have, you see here is billions of these transistors within a single phone. And to make electronics smaller and faster, one wants to make the transistor smaller. And a transistor has something called source, drain, and gate. That's not so important, but what is called the gate and the gate length is what is the number when you compare how small can you make your transistors. And here nanotechnology comes into place because it's about making this material smaller and smaller and smaller. And that's not very easy to do. I mean, there is a natural limit, and that is the size of the atom. And we are actually almost there. This is from IBM, where they show the latest transistor with a gate length of 2 nanometers. That's basically just 20 atoms in a row. So soon we have reached the limit for how small transistors you can make in this traditional way. And I mean, they have changed. This is what I'm trying to show here, from a planar structure to another structure to continue to make it smaller. But soon we will be limited, I think, by basic physics. And then we will have to make other types of computers like quantum computers or biological computers, which we have people within NanoLund. They are working on this. I will not talk so much about this here, but that's sort of the next generation of computers. But already today, I would say that nanotechnology is what we have inside our computers. And now I had questions. I take that later on. It was asking about spinouts. I will come to that. Another example of what I call nanotechnology is that maybe you recognize this. A normal light bulb. I don't know, but I don't have many of these still in my house these days because they have been replaced by something else. And they have been replaced by this. This is light emitting diodes, or LEDs, that you have now almost everywhere, which today, when it's so expensive to heat our houses, maybe we actually miss our light bulbs, but they were not so efficient because a lot went into heat. So now we have the light emitting diodes instead everywhere. And it took a long time before it really went off because people could make many types of light, like red and green, but it was difficult to make the white and blue LEDs until somebody, a researcher, found out how to make these materials. And it's actually material design. And now we're talking about micro LEDs and even nano LEDs. And this is about making materials on an atomic scale to really design the material. I will show you this in the next slide. When you make semiconductors, it's about the atomic level design. And this is something we are very good at in Lund. And now we're not talking silicon, now we're talking other materials, because silicon is a mature technology that we know, but it has its limitations. So what I'm trying to show with these images is that all these small dots are single atoms. And here we see atoms of different material, different semiconductor materials with much better properties than silicon. So to make new technological solutions, you first need to make a perfect material. And this is what happened with the LEDs. So suddenly this technology is now out there. And just to show, because we have so many cool machines in Lund, so we have a machine where we can image when we make these semiconductor structures. And I will show this in this movie. So what you see here is just a droplet of gold. And each row you see building up here is actually an atom layer growing, atom layer by atom layer. And we can now image that. I mean, maybe black and white is not so cool, but it's hard to do color on this length scale. So this is pretty cool. We have reached now that we can manipulate, we can grow, and we can even study what we do, and we call it in situ. So we study the process while it's taking place. And I would say that's a very hot topic in nano research these days with many different techniques. And I wanted to give a few examples of what we in Lund do, what types of semiconductor materials we do, and what we mainly what we want to use them for. So we have a lot of research efforts going on into solar cells based on these materials. So a solar cell consists of something called a p-n junction. We don't have to go into that, but basically we need to change the material, this atom layer by atom layer, to have many different material combinations if we want to take up as much of the sun's light as possible. So the conventional solar cells today just take up a small portion of the sunlight. So the sunlight have many different wavelengths, and we want to take all of these wavelengths. So the most efficient solar cells today, you have to have different materials combinations to be able to gather all the light. So this we have research on, and also doing flexible solar cells. So one might think of solar cells that you can put and be invisible, for example, on your roof in the future, if you for some reason don't like how normal solar cells look like. People are also working on light emitting diodes, as I show here. This is called InGaN, that's a material. And that is, of course, cool for lightning, but it's also cool that if you make a light emitting diode for UV light, you can use it for water purification. So that can be something where maybe nanotechnology can also help a problem today, and also in other countries for a cheaper water purification. I also want to give one more example how we think about nanotechnology and how we learn from nature. Or no, I had one more thing about these materials. So if we talk about electronics and materials, the next thing is the wide bandgap materials. And you all know now about the energy crisis. So we have a lot of devices that requires electricity, and there will be more and more of them. And maybe we don't have enough electricity in the future, and this needs to be tackled in, of course, many different ways. But one thing is to change the conventional silicon to another material, to, for example, have faster internet with lower energy consumption. And then we see here a windmill where you have to convert between DC direct current and alternating current. And when you do this conversion, you lose energy typically. So if we can reduce the losses, we can have faster satellite communication, and we can also reduce the electrical losses when we charge our cars. And we can do this just by changing material. So if we look at silicon, it can tolerate certain temperatures, certain voltages, and certain frequencies. But if we change to these wide bandgap materials, they can tolerate much higher temperatures, much higher voltages, and much higher frequencies. So basically, it's a material question that makes us have a more efficient material so we can have these new solutions. And I think that is pretty cool just looking at the material. So here I see that silicon will always be there, but we will also have these other types of material in the future, and they are already coming a little bit. So now I will talk about how we learn from nature. So this is a really cool project by my colleagues that they started thinking about drones, you know, the drones flying around transporting stuff. What about, can we make them smaller, smarter, and more energy efficient? And unfortunately, we cannot just find it in one of these IKEA booklets how to do this. So we have to think, where do we find the best drones? And the answer is actually in nature. If you think about it, if you have this small bee, it just drinks one drop of nectar, and it can navigate extremely well, extremely efficiently. So then we need to know, okay, how do the insects do that? And luckily, we have researchers within Lund University working on mapping the brain of a bee to look at how are all the signals in the brain going? Why is it so good at navigating? And then we thought, we actually have nanostructures that we can build something like that, that can transfer, in our case, it will be light, that we transfer between our nanostructures to build a drone built on these type of new nanostructures to improve navigation in a drone. So this is now a big EU project, which is a really collaborative project between biologists and material scientists and people knowing about electronics. So I think this is a very good example of nanotechnology, that you work very interdisciplinary to find new solutions and you look into nature for it. I also have to mention a little bit medicine, of course, because that's also a big thing within nanotechnology. And there are so many different things you can do, but in Lund, we work a lot with detection and sensors and also with diagnostics. So the first example is, actually now this is a company called Aligned Bio. So what they have done is they take these structures that you see here. It's these semiconductor structures that I'm talking about. And they can actually be used as sensors as well, because this green thing is a fluorescent molecule, and this is used in medicine to detect stuff. And if normally one molecule is not detectable because you cannot see it, but when this molecule gets attached to this semiconductor structure, this semiconductor will act as a light guide, or think about the prism, like concentrating the light, which means that we can get and detect the signal of just one of these guys. And maybe this is hard to understand, why is that any good? But that means that we can detect the disease much earlier, when we don't need to have that much material and that much signal. So we need much less. And some diseases are like that. Some you have a lot of this to detect them, but with some diseases you have very little to still have it. And to be able to detect this and diagnose this can be very important to get the treatment in early. Another example is where we again make use of nanostructure and its geometry and shape, and that it is on the same scale as things in our body. So here we have again the red blood cells that I said were about 2 micrometers. So if we build a very small channel here with nanostructures or microstructures, when the blood cells go through here, it will bounce on these structures and take a certain route. So what we see here is that the red blood cells are pushed to the wall just by the structures in this very, very small channels. And you also see something green here, and this is a parasite in the blood. And the parasite have a very different shape, which means that the parasite will not be bounced to the edges, but it will stay in the center and end up in a different container. And this is then used to see, did I have this parasite in my blood or not? And why this is so good is that the conventional way of doing this is taking a blood sample, sending it somewhere, put some doctor looking in a microscope, searching for the needle in the haystack or the parasite in the blood, instead of doing this, where you can just take one drop of blood and you can diagnose for this disease or for this parasite. And this is called lab on a chip or precision medicine, that we want to make it easier, cheaper, simpler, that not all countries or everywhere you have access to these labs where you look and characterize, for example, with microscopy. The final example is I have researcher looking at cancer cells and actually looking at how do cancer cells behave on a nanostructured surface and measure the tension between the cancer cells and the surface. And they can see that cancer cells behave very differently from healthy cells. So this can also be a tool to diagnose cancer, and hopefully at an early stage. And then now we're talking about small nanostructures, and we all know that, okay, nano is very small, but our products where we want to use it, they are rather big. And it's actually a very big order of magnitude. If you remember the first slide I showed you with this size scale, I mean, it's very many orders of magnitude when we are looking at here the atomic scale, where we have the single atoms or the molecules or the small nano devices. And then we need to have the components that's on the millimeter scale, and then put these components into bigger systems to build, for example, our drone or our solar cell panel or whatever it can be that we need to build. So we need to get over this assembly gap. And just an example how one can do this with some of these semiconductor structures. Some researchers have invented a technology where we can make these structures in a continuous production way, not in a batch by batch production, but in a continuous way where we actually grow. That's what you talk when you build this atom layer by atom layer. We're talking about growing semiconductor structures. So you can grow them in the gas phase. So they just continue to grow as long as you supply material, and we get a very high growth speed and a lot of material. So that is one key thing when we're talking about nanotechnology. We need to have some method where we can produce a lot of material, and preferably in a reasonably cheap way. Then we need to take this, and in this case, we need to assemble it from atoms to micron. And in this case, it's done by creating an ink with these nanostructures. And then there is a technology where you can align this ink, so you actually start to form thin films. And then you take these films and integrate them into the cells, and the cells into the system. So there are some key things here, and you need to have this cheap and production of a lot of materials, since each nano device or nano particle is very small. And then somehow, preferably with some self-assembly, some alignment, make it into larger structures that you can then work with. But it is possible. Another question one might ask oneself when we talk about this, that I'm sure you might have heard as well. I usually meet two kinds of people. We have the ones really enthusiastic about nanotechnology and the possibilities. And then we have the other ones like, but isn't it dangerous? Isn't it scary? And I think that's a very valid question that we need to take into account. And that's why we work a lot with what we call nano safety. How can we handle and produce nanomaterials in a safe and sustainable way? And the reason I'm showing this image is also why there might be concern, reason to be concerned. So what we have to the left here is a nanostructure, a kind of fiber. And what we see here is asbestos fibers. And I'm sure most of you have heard about asbestos that have killed a lot of people, that cause disease in the lungs. And we don't want to do that. So we know today that we have a lot of nanoparticles surrounding us all the time from traffic and from stuff. But it's actually these fibrous particles we need to be most careful about. And we don't want to repeat what happened when asbestos came. So it was considered this fantastic material. And it was used for many fun applications. And one thing where it was used was in filters for cigarettes. So you can see it was for about 4 years. And it says here, scientifically the most effective filter ever developed to free cigarette smoke of impurities. The only problem is that when you inhaled from these cigarettes, you also inhaled a lot of these asbestos fibers. So I'm pretty convinced that we have learned from history that we don't want to do this again. So people working with nanotechnology also take precaution to, it should be safe for the people working with material, but we also need to think about the end use of material and what is happening here. So we do not want to put nanomaterials as landfill. I mean, this is the worst, when you just put it in the ground somewhere, because we have seen that this, you have heard about the plastic particles and everything ending up. So before we know, that's not a good idea. What people is doing is incineration, and that means you just combust it, you try to burn it. And most of these nanomaterials can actually be burned, but one have to make sure it doesn't get released with the exhaust gases. And I have had colleagues looking at this to make sure you need high enough temperature and so on. And the best thing is, of course, to look at recycling. And we can do that. We're trying to work with this safe and sustainable by design. So if we look at the waste hierarchy, of course, the best thing is if we can reduce things, reduce the waste or reuse our materials. But it's also pretty good if we can recycle them. So what me and some colleagues looked at was carbon nanotubes. This is a nanomaterial I will explain in the next slide a bit, but a very promising nanomaterial that you mix in with plastic to make the plastic better in certain ways. And normally a way where you can recycle plastics is by pyrolysis. You evaporate or you heat up, so the plastic evaporates away, and you can take care of that. And then we wanted to see, can you do that and also maintain the carbon nanotubes and make a new material out of them? And this is just a pilot study, but it seemed that it was possible to do this. And if we talk about carbon nanotubes or carbon material, this is also a very common nanomaterial. We're not working so much with that in Lund, but for example, Chalmers work a lot with it. So you might have heard this Nobel Prize for graphene. That's just a single layer of carbon. And if you roll that up, you get the carbon nanotube, and you can have just one wall or several walls. And these carbon nanotubes and also graphene are often used as filler materials, for example, in a polymer, to increase electrical conductivity or actually add electrical conductivity that you don't have, or mechanical strength or thermal conductivity. And you can actually find this in products already. So there is a company making tennis rackets and skis where they claim they put graphene in. I would doubt it's actually single layer graphene, but it's still on the nanoscale, and they do this to have stronger and lighter materials. And there is actually a lot of application areas of graphene or carbon nanotubes as these fillers where you make these composite materials that you can see here. Because again, you want to improve mechanical strength, conductive properties, shielding properties, and you can use it for sensing technologies. For example, if you have a carbon nanotube as a sensor, you might want to embed it in your larger materials so you have some kind of self-sensing in the material as well. So if we finish this first part where I talked about nanotechnology, I hope I managed to show you that it provides some unique opportunities, for example, energy solutions, not only solar cells, but with new technology, new materials that can help to use our energy in a better way, but also to harvest energy, of course. Nanotechnology is also believed to be very good for different sensing applications. So it can be efficient gas and biosensors. I hope I've shown you it's been good for this lab on a chip or precision medicine that can hopefully help many people, and also for water purification, for example. So this is just some areas we work with in Lund, and there are tons of different areas within nanotechnology, but this is some of the areas we work with. And the way we do that is that we have this strategic research area called NanoLund, and we get funding directly from the government every year. So we have gathered within Lund University, we're about 250 researchers and 150 PhD students. And it says here, in an open collaborative environment. I think this is the key thing, that we work together across boundaries. So we can just see here that 3 faculties are involved: the engineering faculty, LTH, the science faculty, and the medical faculty. And then we have just different divisions within the different faculties. But you can see it range from nuclear physics to clinical sciences and neurology, for example. So it's very interdisciplinary where we work together. And in the end, it all comes down to the people, the researchers, I think, that are so many bright people with good ideas. And when you take all these people and put in one place together, as we do sometimes, immediately you will have these new crazy ideas, like the drone inspired by the bee brain, for example. So we are always asking ourselves, what can we do for society? So we want to have a sustainable society and a pathway to the future information society. I mean, we have colleagues working on this 6G and related things, and then precision medicine for the many. And we have looked at how we can impact business and society. And we want to work from fundamental to applied research, because it's very important with this fundamental understanding if we are going to make a difference also for the applied research. And the key here for us is the atomic scale materials control, and that we learn from and we work with nature. And we have some core competences, and I would say it is compound semiconductor structures. And we also have a strong field in nano and quantum devices, and to fabricate, characterize, understand nanotechnology. We have something called Lund NanoLab, and we also have Max 4 that is closely related. And we also, of course, many of us do fundamental research, including myself. But we would also like to see our research go into products. So this is a little old, from 21-22. We had 15 spin-out companies in operation that somehow has come from this environment. And as with all spin-outs, some of them make it and some of them, they die again. And I think this is the nature of spin-out companies. But we do have a culture where we want and encourage people to actually make something out of their ideas. And then we also have a lot of collaborations and networks with established companies. I think as a researcher, it's very easy to think that, okay, here is the problem, now I want to solve it. But then it turns out that was not the problem at all. So sometimes it's actually good to talk to the established companies and see what is their actual problem, where do they need help, how can we work together to solve something that they actually need help with. And I would like to finish by saying that Lund right now is a wonderful place to work with research and nanotechnology. What you see here on this image is Malmö, where I'm actually sitting right now. But we should focus here on Lund, where Lund University is. And then we have ESS and Max 4. As you maybe know, Max 4 is already up and running, and we're using that a lot. And then we have ESS being built. And these are really big facilities for characterizing material. So what we are working on now is building a new nano lab that should be in between ESS and Max 4, because currently we have sort of grown out of our lab. And it's also planned that part of the university should move up here, large parts of physics and chemistry. When that happens, it's hard to say. Lund University is a big university, so some things don't go as fast as they could. But there are already companies establishing their R&D up in this area called Science Village. So I think that nanoscience and material science in general have a very bright future in Lund. And with that, I would like to thank you for your attention, and I will try to answer questions here, if you have any. I see the next hot technologies that will be spin out from NanoLund after aligned bio. I think that maybe this, what they have looked at this with this insect brain, maybe not to build drones, but this idea to actually use light for fast transfer of signal might be a very hot, cool technology. And then I'm sure there are many other technologies as well. Yes, now I got a question about a lot of people scared about nanotechnology, not from a waste problem, but from abusing the technology. And I think that this is always the question with new technologies. How can you use it? I mean, a knife is really crucial for me when I cook, but it can also be used in bad ways. And I think all research today, I'm thinking about artificial intelligence and also this, how we can go in and change in our DNA and change in our bodies. I'm more scared about this. And I do think that people doing research on ethics and thinking about how to use technology is also extremely important to think about. And I do think we have, that's why it's good to work at Lund University, where you have researchers within many different topics. So the fear of nanotechnology being used in a bad way, of course, I think all technology can, but I think there are other technologies I'm more afraid of personally.
Thank you so much, Maria. I'm following the chat, the Q&A, but I have it a bit far away from me, so I have difficulty seeing.
Okay.
Seeing what it says. We have quite a few people thanking you very much for a very interesting lecture. Then at the bottom, if you would like to go in and look at the Q&A, I think there might be 2 questions at the bottom there as well.
Yeah, there is one about 6G and wireless communication. There is a division working a lot with that. Lars-Erik Wernersson, I would say, is the leading professor doing this. I am sure that if you go to NanoLund's homepage, there will be a lot of links covering there. You can find all of the different research activities that we have. I also have a question, radionucleotides and nano application. That is nothing I'm aware of is being done in Lund. Maybe we can write, did I not? Maybe you have this, I think it's just nano.lu.se, that's our homepage. It's a bit embarrassing, I don't know this, but I have it as my starting page on my computer. So but there should be links to all the research we do and divided in all the fields that we cover.
I will put a link in the chat.
Yes.
Just a short while. And then let's see.
There's one. What about nanorobots inside our bodies? It depends on how you define a robot. I mean, people are looking at how can you transport nanoparticles filled with medicine to a certain place in your body and make it release the medicine to treat like the specific point and not the entire body. And that, do you call that a nanorobot or not? I don't know, but people are working on this. There was something, nanomaterial has the lowest friction characteristics. That I honestly don't know. I'm sorry about that.
I'm chasing around the link, but I will include that in the in the email with the recording as well. I actually had a question for you, Maria, if you don't have any other in it's about workforce needs. What do you see are the skills and educational areas we need to people need to study in order to be able to meet all the demands from when nanotechnology is growing. Many new jobs. It sounds like many new jobs can be created from this research. What skills do the workforce need to get in order to be?
First of all, I do think that all of us needs to stop talking about mathematics, physics, natural science as something scary and difficult and impossible to learn, so that our kids realize it's fun and are not scared about this. That's a good start, because I do think we lose a lot of talented and good people very early in the school years. Then if we go more into the actual what is needed, I would say that in semiconductors, people working on hardware semiconductors, I mean, we have a lot of software programming, but we also need to build the hardware, build these semiconductors. And I do think that it's very easy to get a job also in Sweden if you have these skills today. So that's one area I think of immediately.
Thank you. Yeah. Did we have anything else in the Q&A before I?
There was somebody that want to collaborate on water splitting. I think that you should go to the NanoLund homepage and see is there any research closely connected to what you do, and then contact the person, the name of the person there, and then they will guide you to the right researchers.
Great. Are there any other questions from the audience? You're welcome to write them now. If not, I'm also curious about when you're talking about, you showed collaborations, well, that was mainly in Sweden. What other countries are Sweden working with when it comes to nanoscience and research?
I think we did a mapping of this to actually see the main countries for collaborations, and the easy answer is a lot of them. I have colleagues going to Africa to do measurements, for example, but also the standard, a lot of collaborations with the US, with Denmark, also Asia, of course, although it's a bit tricky today, maybe with China, but there are collaborations with also other Asian countries and a lot within Europe. So I would say that most countries, or many countries at least.
Exciting and challenging, I can assume. No, I think we've answered all the audience questions. If you would have a final question, what would be the most exciting finding in your case? What would be the most exciting finding within nanoscience for you, Maria?
Oh, wow, that's a
$1 million question.
I work on small nanoparticles for catalysis and also for magnetic materials. And I would say to make an improved catalyst for some important reaction where you can really reduce the amount of catalyst needed and the energy needed to catalyze certain reactions. For example, when you make certain drugs, you need a lot of, it's very expensive, you need a lot of material, it's not so efficient. So to find a material that it works really good as a catalyst for, yeah, depending on the area, but where you can make a big difference.
Great, let's hope for that. I think we are getting close to 1 o'clock. I would like to say thank you so much, Maria, for joining us this lunch hour. I think it was very appreciated among both for me and also for our audience. For our audience, thank you for joining, taking your time to learn more new things. And you will receive an email from us within a few days' time with the recording and useful links and such as well. So thank you so much, Maria. I will close down the webinar, so we won't meet more today either, but we will keep in touch as well. And for those of you, if you have any questions, send an email to info@alumni.lu.se, and have a good afternoon, everyone. Thank you for watching.
Thank you. Bye-bye.
Bye-bye.